Okay, hello everyone. So we'll start in 4 or 5 minutes. Let others join, let a few others join, and then we'll start the session. Okay, thank you for joining. Okay, let's start with the session. So hello everyone, I am Somnath, a second year PhD student, and this is the 8th week of NPTEL live session on CS100 operating system fundamentals. In this session we'll be studying a few problems and theories related to TED logs. So let's go ahead with the problems. So I hope my voice is clearly audible to you all. If there is a problem, you can use the chat box as always. Okay. So this is the first question. That is, there are five processes. Sorry, P0, P1, P2, P3, and P4. And considering mutual exclusion, hold and wait, and no preemption to be valid, which of the following cases leads to a deadlock? That is, P0 is waiting for a resource held by P2, P2 is waiting for a resource held by P3, and P3 is waiting for a resource held by P1. The second option is P0 is waiting for P1, P1 is waiting for P2, and P2 is waiting for P3. Third is P0 is waiting for P2, P2 is waiting for P4, and P4 is waiting for P0. And fourth is P0 is waiting for P1, P1 is waiting for P3, and P3 is waiting for P4. So yeah, I already have one answer, that is option C. Anybody else would like to contribute? So we are considering that the mutual exclusion can be a case. Hold and wait also exists in this circumstance, and no preemption is also present. That is, once a resource is given to some process, it can choose to the process may choose to not go into preemption. So yeah, there is no preemption, and thus the resources that is held by one process will not be freed until and unless the process chooses to do so. So yeah, we just have to consider the case of circular wait. Then if you have followed the theory of deadlock, there are four conditions for holding a deadlock: mutual exclusion, hold and wait, no preemption, and circular wait. So we just have to consider that fourth case. So which among the following options do you think is correct, that is holds that circular wait condition? I'll just wait for another minute or so if somebody wants to answer. Okay, so this is the first question that we are discussing. That is, we have five processes, and we are considering that mutual exclusion, hold and wait, and no preemption exists. So which among the following situations lead to a deadlock? P0 is waiting for a resource that is held by P2, P2 is waiting for P3, P3 is waiting for P1, P0 is waiting for P1, P1 is waiting for P2, and P2 is waiting for P3, P0 is waiting for P2. Okay, so okay, I'll go to the answer now. So yes, the third condition leads to a circular wait, and therefore yeah, it leads to a deadlock. So all the three other conditions already exist, so that leads to a deadlock. So going to the next question then. So this you may know from the diagram, it is a resource allocation graph. Okay, so considering this resource allocation graph, which of the following is true? Does there exist a deadlock in this case? There may be a deadlock, there is a deadlock, or it can't be determined. So which among the following do you think is true? Okay, I have one answer. I have two answers. Anyone else? Okay. So this is a question from Galvin, the book from Galvin. So what happens in deadlock is, there just isn't simply a case of circular wait. If there exists a circle in the cycle in the resource allocation graph, it may not always suggest that there exists a deadlock. You have to see, is there a possibility of the processes executing without a deadlock? So let's consider the processes one by one. So P2 is having one instance of resource R1. So you have to I think you have assumed that the resources are not shareable, that is R1 and R2, the instances of the resources that cannot be shared among processes. Okay, so one instance is with P2, so P2 does not need to wait for any other resource, so it can just simply continue executing and complete up till termination. So then one instance of this resource is free, P1, which requires one instance of R1. It was waiting for one, so this instance of the resource R1 is free, so it can use up that, and it already has one instance of resource R2. It thus has all the requirements satisfied, and it can go on till completion, right? Consider the case of P4 now. So P4 does not require any resource, it already has its resource allocation satisfied, requirement satisfied, so it can go on to completion. So all the other processes have completed, just P3 is left. It has one instance of R1, it requires one instance of R2, so there are no other processes there in the system, so both the instances are free. So obviously it can any of one of the instances can be allocated to P3 and it can go on till completion. So there exists a cycle, but it does not lead to any deadlock, right? So option A is correct actually, that is, there is no deadlock, everything can go on till completion. There exists a case of wait. P1 and P3 are the processes that need to wait for P2 and P4 to complete, but as we can see from the graph that there is no instance of P1 requiring more than what is indicated by this resource allocation graph. So ultimately there is a situation when once we consider up to infinite time, P1 will go on till completion. Like if we consider in infinite amount of time, at some point P2 will complete and P4 will complete, and that leads to P1 being completed and P3 also being ultimately completed. So there is no deadlock. So this is an example from the operating system book by Galvin. You can study it there also. Okay, let's go to the next question. Okay. So before that we'll study the conditions that lead to deadlock. See, this is a resource allocation graph that contains a deadlock. Okay, so there is a condition, there is a situation of circular way, and it has ultimately led to a deadlock. Okay, see, what mutual exclusion says is that these instances are not shareable. Okay, so hold and wait says that it suppose the process P2, it is holding one resource and it can wait for, it is holding at least one resource and it can wait for more than one resources. So that is true for all the three cases processes. No preemption says that once it reaches the state of that it can go to a situation of deadlock, none of the processes can be preempted, that is, none of the processes can be sent from the running state to the waiting state or the ready state. Sorry,
I have a question, can I ask?
Yeah, sure.
Yeah, I mean, suppose if there is a code and there is a shared resource, and the code is allowing a process to be in the critical section,
to be in,
I mean, one by one.
Okay.
So in that scenario, will there be a deadlock if there is a one single resource?
No, it will never be a deadlock, because it is just allowing the processes one by one, right?
Okay. No, like suppose if the one process remains in the critical section indefinitely, and the other process is just about to wait, change the variable and then come into for the critical section only if the first process comes out.
That is okay. So the considerations for all the theory that we are studying here is that a process has to complete at some instant of time. It can go on. It cannot go on up till infinity, right? So once a process goes on up till infinity, there obviously arises a condition of deadlock, but that is not the assumption. We can
I just want to know the difference between busy waiting and deadlock situation, because in deadlock situation I think if there are more than one resource, and one resource is suppose there are two processes, and for resource first process is wanting resource 2, which is holded by process 2, and process 1 is holding resource 1, which is again required by processes 2. So I mean each from each other they are wanting, and they are not allowed to free the resources, then only there is a deadlock. But if there is single resource and a process is holding it indefinitely, then it will be a busy waiting kind of situation, but not deadlock.
No,
I mean,
busy
I just want
waiting
to
is a
understand the
different
concept.
kind of thing. Busy waiting means that the process, with reference to critical section, it cannot go into the critical section, and it cannot progress with the situation also. It is never able to go into its critical section, and without going into the critical section, it cannot make progress with the process, right? Overall process. So what happens is that it is kept waiting.
Yeah, I mean, so in that case,
Yeah.
there will be no deadlock, right?
No, that is not the case of deadlock.
Okay.
Yeah.
Actually, there was a same question similar to in the gate examination, and it was confusing. So this I learned clarification.
Okay.
Thank
Okay. Anyway, okay. Let's progress with the next question then. So this is a comparatively more complex resource allocation graph, but you'll see it is simpler. So the task is again the same. You have to check whether there is a deadlock, there may be a deadlock, there is no deadlock, or it can't be determined. So which of the following options do you think is correct? Anybody wants to contribute? Okay, I've got two answers. Anyone else? Okay, three answers. Anyone else? Okay, let's study this graph for a bit. So the process P4, it does not require any additional resources, right? Okay, so the process P4 does not require any additional resources, right? So P4 can go up till completion. Same is the case with process P2. It can go on up till completion, right? So does there exist a cycle, by the way? Does there exist a cycle? So there exists a cycle. See, this one is the cycle, right? But anyway, since P2 can go up till completion and P4 can go up till completion, so there will be instances of the resources that will be free, which will be utilized by the waiting resources, right? P1, right, like P1 can utilize that instance of R3, and the cycle will be broken, and ultimately there will be no deadlock. Okay, so yeah, let's move on to the next question then. Again, the work is same, task is same. You have to determine whether there exists a deadlock or not. Although the graph looks more complicated, but it is simpler actually. The problem is simpler. So the first condition that it needs to hold is that there should be a cycle in the resource allocation graph. That is what you need to find first, whether there exists a cycle or not. Okay, I got one answer. Anyone else would like to contribute? Okay, let's study this graph for a bit. Anyone else would like to contribute, by the way? Stay waiting for answers. If not, we'll proceed. Okay, let's study this graph. Deadlock, for the condition for deadlock, it should be a circular weight. There should exist a circular weight. So first, let us see whether there exists a cycle or not. So if you examine the graph carefully, you will see that there exists no cycle, right? Like the process P3 is you can see the process P3, it actually has all the resources that it requires, and there is one instance of R3 actually free, which can be allocated to P2 or P1. Okay, if it is allocated to P2, then P2 can move on up till completion, and then it can be allocated to P1, right? So yeah, there exists no deadlock in this case also. There exists no cycle actually in this case, so no question of deadlock. Okay, let's move on to the next question then. So in this question, you have to select the incorrect statement or statements with respect to safe and unsafe states. Sir might have taught this figure in class, so with respect to this figure, you have to answer the questions. That is, a system in safe state can't have any deadlocks. A system in unsafe state has at least one deadlock. A system in safe state, a process Pi can request a resource that is currently held by process Pi plus 1, and a system can transition from safe state directly to deadlock state. Which are incorrect? Which is or are incorrect? There may be more than one. Okay, I got one answer. Anyone else would like to contribute? Anyone else would like to contribute? Still waiting for answers. So what happens in deadlock state is, yeah, I got one more answer. So what happens in deadlock state is, there are four conditions for a process to be in deadlock, for a system of processes to be in deadlock state. One process can never be in deadlock state. So there should always be a system of processes according to the conditions laid down, right? And a process a system is in unsafe state when there can arise a condition which may lead to a deadlock, right? There exists a resource requirement there that can ultimately lead to a situation that is a deadlock. Okay, and when a process is in safe state, you know what is a safe state. That is, the resource requests. There may exist some resource requests in the unsafe state that may not be fulfilled by the current situation of the system, and in the safe state the opposite happens, that all the resource requirements that can come all will be fulfilled by the system, or can be fulfilled by the system, that so that all the processes can progress ultimately. Okay, so yeah, actually these three statements are incorrect rather. So yeah, a system in safe state can't have any deadlocks, that is correct. A system in unsafe state, it has not yet had a deadlock, but yes, there can be a situation of deadlock in future. That is, as I said, in unsafe state, the resource requests that can come, it may be the case that it cannot be satisfied given the resource instances that are present at the moment. Okay, so That is the thing with the unsafe state. And in safe state, always a process pi, it will always it can request a resource that is currently held by a process that has started before it. That is I it cannot be I plus 1, it has to be I minus 1 or something like that. It has to be the other process should have started before. And a system can transition from a safe state into unsafe state, and then only it can go to a deadlock state. It cannot directly transition from a safe state to a deadlock state. That is why we have the boundary of unsafe states. Once a process system goes into an unsafe state, the operating system becomes aware that it can go into a deadlock state, and it takes the necessary measures, okay, prevention, avoidance, and things like that. Okay, so this is an instance of a resource allocation graph which shows the safe and unsafe states. So this system is in safe state. Okay, so it shows that it can request for the process resource R2, both the processes, but it has not yet made the request. Okay, and it this process has made the request for resource R1. So P2 has made the request for resource R1, and P1 already has an instance of the resource R1. Okay, so this process is in safe state because P1 has no requirement of any other resource at the moment. It can progress, and once R1 is free, P2 can utilize that. But once R2 once P2 has made the request for R2 and R2 is already allocated, then it goes on to an unsafe state, because in future, since P2 has P2 can request for R2 in future, there that situation, if that arises, that P1 can request for R2, and if that situation arises now that P1 has requested for R2, that leads to a deadlock, because this one is held by R1 is held by P1, and it is waiting for R2, which is held by P2 and waiting for R1. So that there is a cyclic wait, and it ultimately leads to a deadlock. So this resource allocation graph clearly differentiates between the safe and the unsafe states. Anyway, let's move on to the next question. So it's a pretty simple question. So PA, PB and PC are a set of processes. So with A equals to 23, B equals to 12 and C equals to 75. So accordingly you have to and all of the three require the same resource to execute. So to ensure a safe state, which system is actually correct, that is P3 PC has to wait for termination of PB, and PB has to wait for PA. PA has to wait for PB, and PB has to wait for PC. PB has to wait for PA, and PA has to wait for PC, and PC has to wait for PA, and PA has to wait for PB. Which among the following do you think is correct? Is a correct system? I am waiting for answers. If anyone would like to contribute. Okay. Generally, we start a lower process number signifies that it has started earlier, and the process that has started earlier, we look to complete that earlier. So keep that in mind. And these the lower number actually signifies the when it has started. That is, lower the number, it has started earlier, obviously, right? So that is what happens in Unix. You can actually see, if you start a process with fork, you can actually see that it has the child process has a greater process ID compared to the parent process. You can actually see using get PID. In Unix. So anyway, let's move to the answer. It is also, anyone else would like to contribute? Okay. has greater, like E has the smallest index, A is comparatively bigger than C. Does that help? Anyone else would like to conclude? Okay, anyway, let's move to the answer. The actual answer is actually D. Yeah. Okay, so PC has to wait for termination of PA and PA has to wait for termination of P. That is the answer. Okay, so let's move on to the next question. So now we'll go to the Banker's algorithm. So it is used for, can anyone say what is it used for? Deadlock prevention, deadlock avoidance with single instance resources, deadlock avoidance with multiple instance resources, or deadlock recovery. Okay, I got one answer. Anyone else? Okay, I got two answers. Anyone else? It's a pretty simple question, right? I'll wait for a minute if anyone else would like to contribute. Okay, it's option C. Simple, pretty simple. So anyway, let's move to the next question. This is with reference to the data structures that are used in Banker's algorithm. N signifies the number of processes and M signifies the number of resource types here, as I said. So which is or are correct? There may be multiple correct options. First option is available is a vector of size M. This is with reference to the theories of Banker's algorithm. Okay, so available is actually a data structure. If you remember, max is a data structure, need is a data structure, allocation is another data structure. So available is a vector of size M. Max ij signifies the maximum number of instances of process process pi may request of resource rj. Need ij can be greater than max ij, and need ij can be greater than allocation ij. Which is or are correct? Anyone would like to answer? A, B. Okay. Okay. So available signifies that how many instances of the resources are available for use now currently. Okay. So it is a vector of size M, right? Since there are M resources, M types of resources, so and each resource can have some number of instances free, so it is a vector of size M, right? What does max signify? Max signifies that how many, and at maximum how many instance of a resource J can a process I request at a single point of time. Okay. What does need signify? Need signifies that it already has some resources and how some instances of resource rj, process pi already has some instances of resource rj. How much more should it require to complete, in order to complete the process pi? So max signifies what is the maximum instance it requires, the process pi requires of each resource. Need signifies what can how much more it requires than it already has of each instance of each resource rj for completion of the process Pi. And allocation, as usual, signifies that what is the allocation for process Pi of resource Rj. How many instances of resource Rj are already allocated to process Pi. Okay. So yeah, just the third option is incorrect. Rest all are correct, because need can be greater than allocation. What instance of yeah, what how many instances are current of resource Rj are currently allocated to Pi that can be lower than what it actually requires, right? So this can also be true. Anyway, I hope I was clear. If anyone requires any further explanation, you may use the chat box. Okay, so let's study a theory related to this. So what available signifies is that it is a vector of length m, as I said, and if available j equals to k, signifies that there are k instances of resource type Rj that are available. Okay, max is an n cross m matrix. So this is a vector of length m, and this is a matrix of length of size n cross m. So if max I comma j equals to k, then process Pi may request at most k instances of the request Rj. So this is the maximum limit for process Pi for instance for a resource type Rj, right? So need, what does need signify? That if it is equal to k, then process Pi may need k more instances than what it already has of resource type Rj to complete its task. So it can never exceed max, as can be seen, right? And allocation means that how many number of instances of resource type Rj are already allocated to Pi. So in equation form, need of Ij equals to max of Ij minus allocation of Ij. So this can exceed this, but this will never exceed this, right? As can be seen from the equation. Okay, let's go to the next question. It's a simple question now. If allocation of 3,2 equals to 6, it signifies what? So there is a generic data structure that we are using. What does it signify? If allocation 3,2 equals to 6. Okay, I have one answer. Anyone else would like to contribute? Okay, I have 3 answers. Okay. Okay, it's pretty simple question. So yeah, A is correct. That is, process P3 actually requires 6 instances. Has been allocated 6 instances of resource R2. Anyway, so this is a question of Banker's algorithm. So you need to solve this question. That is, solving this question means you need to determine the sequence of completion among the processes. So the allocation matrix is given, the maximum requirement matrix is given, and the available vector is given. So how do you already know how to calculate the need matrix from the allocation and max, right? It was there in this question, so it was here. Okay, so anyway, let's go to the question. And yeah, first calculate the need matrix. I'll give you some time, and you do not need to answer in the chat box now, so because it will be a matrix, it will be a long matrix. If you have completed with the need, with completion of the calculation of the need matrix, just say yes or something in the chat box. We'll go to the next slide. First step, you have to calculate the need matrix. Please do so. I'll give you some time to calculate this. if you have completed, you may answer by saying yes or something so that you can move on. Just need to calculate the need matrix for this part. If anybody has completed the need matrix. I'll wait for another minute. Okay, let's go to the answer, first answer. So this is the need matrix. So this is the need matrix, right? So what is done is simply max minus allocation. So as can be seen that need can be greater than allocation, but it will never exceed max. Okay, so so what you simply do is you subtract, so it results in 743 and 122 and then 600 and then 011 and 431. Okay, but what is how many instances are available is 3, 3 and 2. It is not given to any process, or it is not assigned to process P0 or something like that. It's just that for solving we have written it here, but so that is the available matrix. Anyway, let's now get into the steps required for solving this problem using Banker's algorithm. So this is a screenshot from the slides that are used in the theory section, in the theory of the course. So in the lecture videos of the course. So I just used a screenshot from there. So let me just give you an overview of what you need to do really. So there are two arrays, two vectors that you need to use: work vector of length m and finish vector of length n. So that is what you ultimately need to use, and that will do your work. Okay. So at first you need to initialize work equals to available. So at first work will be equal to 332. Okay, and finish of everything will be false for all the processes. So finish of 0, 1, 2, 3, 4 will be false. Okay, so that is what you need to do at first. That is simple. Step 2 is you need to find such an I whose for which finish of I equals to false and need of I is less than work. Okay, so need of I, okay, need of any of the processes, that should be less than work, that is currently it is equal to available, that is 332. So for all the instances, need of I should be less than what is available. That is one. That is how what you need to find. And if there exists no such process I, then you have to directly go to step 4. And if there exists something, then ultimately what will happen is that what is available will be satisfying the need of that process. So then that process can use up those available instances of those resources, and then it can go on up till completion. And then whatever it had and whatever it needed on extra, all those resources, all those instances of all those resources will be free now. So the available will will ultimately increase. And by how much? So at first what you need to do is available minus need. That will result in the currently available resources when a process that has been scheduled for running has left available. So after that process has completed its execution, it will release all the resources that it was holding. Therefore, with that current, you have to apply. You have to sum max. Instead of applying that two-step process, you can directly what you can directly do is you can directly sum the available with the allocation. So what this signifies is that before the need was satisfied, this amount of resources was available, and after the process has completed, whatever it was already holding, all those resources will also be added. So that is what we are doing here. We are simply adding the allocation with the available. So that is what will happen. So work will currently be work plus allocation, and finish of that process will be true. And then these two will work in a loop until and unless all the i's are complete, or we go to this condition, that is directly go on to step 4. And in step 4 we will simply see that if all the finishes are equal to true for all the processes, and otherwise if there exists at least one process for which finish of I equals to false, then it is in an answer state. So yeah, make use of this algorithm and please solve the question. I will give some time because it is a lengthy process. So yeah, take your time. I'll give 5 minutes or so for solving the question. In between, I'll help you with the steps. If anybody has completed, you may can respond with yes or something. You may respond with the sequence of processes. So we have an answer here, right? So sequence of processes, you need to answer that what is the completion sequence. The algorithm, I hope this is simple enough. Let's go to this will be more helpful, I guess, if you have not noted it. You need to compare available with need. If need is lower, you need to sum available with its allocation. That is what we need to do, simply. So I'll give it a minute or two and then we'll go to the solution process. Okay, we'll solve the problem. I hope my voice is clearly audible. If there is a problem, you may interrupt in between. So at first tell me, what is the first process that will be completed? Anyone? What is the first process that will be completed? So you need to go in sequence, right? Don't pick a random process. Just check with P0, then P1, then P2, then P3, and then P4. Don't just pick up a random process. So, yeah. So just tell me what is the first process that will be completed. Anyone? P1, then false state P2. Okay, 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 go on. That's good. So what is the second process that will be completed? Okay, what will be the work vector after process P1 has completed? Can anyone say that? What will be the situation of the work vector after process P1 has completed? At first it was 3, 3, 2, right? I'll also start solving. So after process P1 has completed, what will be the work vector? So what will be summed is 2, 0, 0 with 3, 3, 2. So it will result in 5, 3, 2, right? Then can P2 complete? No, it cannot complete. It will go to P3. Can P3 complete? Then 0, 1, 1 is the need of P3 and we currently have 5, 3, 2. Is it okay? Is need less than what for P3? Waiting for answers. One thing is available will always keep on increasing. It will either stay the same or it will keep on increasing. It will never decrease because you are just adding up things. You are never subtracting anything actually. right? So it will keep on increasing. That's a sanity check kind of thing. If you have made a mistake in between. Okay, P2 is true and P3 is no, P2 is not true. So we have 532 in between. So P2 requires 600. So P2 cannot go on to execute, right? So check the need of P2. It is 600. After completion of P1, we have 532. So 5 is not less than 6, right? So P2 cannot complete. According to my calculations, P3 will complete next. Just check once. Okay. Check with the need, add with allocation. Check with need, add with allocation. That is what you need to do simply. I am just getting one answer. Anyone else would like to contribute? Yes, I got another answer. Anyone else would like to contribute? Yes, that is correct. Yes. So after that, what will happen? Add with allocation. Check with need, add with allocation. Okay, let me do one thing. Since we are nearing the ending part, I have one more question left actually. So I have given the solution in the slide. So you need to study this. This is the correct sequence. So there are steps also given accompanying. So these steps relate to the steps of this algorithm. Okay. So you need, if you follow, you can hopefully. You will have no problem. If you have any problem, you can use the discussion forum, or you can tell me next day. Yes, P3 and P4 are true. Yes, and then you need to reiterate again over the processes that are not yet complete. So this is the sequence. I was running out of time, so I came to the answer. Okay. So anyway, we have one last question that is related to deadlock recovery. So how should we choose the order of process termination once we have faced a deadlock and are trying to recover from it? So how are we placing the criteria for process termination? So that is based on the number of processes to be terminated. So that is based on the processes priority of the processes to be terminated, or is it required for is it the time required to complete for the processes to be terminated, or all of the above? Okay, so very good. Last option is correct. All of these are correct. Anyway, try to solve the banker's algorithm problem. If you require, I will try to give another problem on banker's algorithm in the next session, or I will. If you are facing any problems, I will Please tell me at the beginning of the next session. We will discover. Yeah, explore the solution once again. Okay. So, anyway, thank you for joining in the session. I will be uploading the materials as usual. So yeah, thank you for joining. Hope to meet you in the next session. You may drop off now. Yeah, thank you.